Today in next lecture we will be talking about query optimization, and I alluded to that already multiple times throughout this lecture. So what we've learned so far is concrete applications and concrete concepts of query processing, be it ER model, relational algebra, SQL and so forth. So very super fundamental concepts. But now that we look at the question a little bit, okay, nice, but what if the data gets bigger? How do we actually get from SQL to an efficient program? SQL is not a program. It's a declarative way of describing how the result, how the data should look like. And the job of the database system is to find out, okay, how do I get from SQL to such a program? And that's what this lecture and next week's lecture will be about. And there's a stark difference in SQL engines, or however you want to call that, systems that process SQL, systems that allow you to create a schema and then query the data in that schema. And there's a huge difference in the performance of those systems. And the system has a lot to do with what is called the query optimizers. When you look at relatively simple systems like SQLite, which is a great system, don't get me wrong, it's more comparable to a yacht, like a sailing boat. Not so fast, but it does a job. You can get so and so far with that, but it's not that fast. But probably it's good enough for many tasks. Actually, SQLite is the default engine in many web frameworks like Django, for instance. MySQL is another database system or a SQL engine, however you want to call it, that's already a bit faster, like a small motorboat. Then there's most widely used, the most popular open source system, that's PostgreSQL, that brings you very far, has a ton of features, hard to use, all of these features, absolutely crazy. But then compared to that, there are modern database systems that incorporate the latest research, can fly like through wormholes, have a warp drive and stuff like that. So this is all fancy and this is cool, but maybe for your average use case, you're not going to need this stuff. You will be good enough, you will be good with the Postgres Jumbo Jet or the MySQL motorboat or the SQLite yacht. So it really depends on the use case you're having, and you have to be careful to pick the right system. Okay, so we look at what do we do to get from SQL to an executable program in principle. What are the steps taken there? And there are different ways how to explain that or how to engineer that. So this is one way of doing that. There are others, but I think this is a relatively simple approach, and that gets you pretty far. So the following slides will all be presented along this schedule. So we have SQL that's coming in and executable code coming out. And as usual, there are some intermediate steps here that are being taken. There's some sort of annotated relational algebra. So SQL is actually translated to something like relational algebra. Then we have what's called a transformed logical plan, and then we have what's called a physical plan. I will get to the details in a moment, but basically it's a compilation process, very similar to compiling C++ to an executable. Not just that we don't have C++ here, it's SQL. It's a domain-specific language being translated to an executable program. And the good thing is, well, you don't have to know about that. The user of a SQL engine / database system doesn't have to worry about them unless things go wrong. Systems can do mistakes, can run into performance traps, and then you better understand what the heck is going on. / as a computer scientist, you should always understand in principle what's going on under the hood. It's not about, oh, I'm just using that and then there's some magic happening. No, that's not computer science. Computer science is understanding, at least in principle, what's going on in the machine on all levels. That's why we're doing these lectures. And depending on these, on the query optimizer, so the query optimizer is the component doing this translation here. Some of the translation steps can be very simple, with simple heuristics or even with cost-based optimization. But first things first. So this is what's called a canonical translation. It's also described like that in several textbooks. So you basically translate SQL to relational algebra in a one-to-one stupid translation. So if the input is something like that, a standard SQL expression with a couple of projected attributes, aggregation functions, our tables, the where clause, grouping conditions, and maybe a having condition towards a group, you can blindly translate it to the expression on the right. Again, if you recall the order in which a statement is executed, so we first do the from part here. It's just blindly combining all of the data via cross products, binary cross products. You could also write an n-ary cross product with all the relations from R1 to Rm. Doesn't make a difference. Then conceptually, after the cross product, there's filtering. So that's the where part here. It's the second part. Then next step is grouping or group by, including already the projections, the 3 steps we learned about. That's this part and also this part if you want. But then there's this additional filter. That's what's expressed by the having predicate P2, and then there's a final projection. And that's basically the one-to-one translation you could do. So if you do it like that, you can then build on that translation. A couple of other things you can do along the way is you handle views. If you recall what we learned about views, a view is just an alias in a database. It's never executed when you define it. So if you write create view, it's just a shorthand, just a symbol being defined. Yeah?
I'm missing keyword distinct from the SQL query because
yeah. Very good observation. So here you have to be careful. Yeah, you have this set semantics in SQL, and you have multi-set semantics in you have multi-set semantics in SQL, and you have set semantics in relational algebra and relations. So you have to be careful in these translation steps. Yeah? So you could make the argument here, you better write a distinct here. Distinct, because depending on your schema, on the left there might be duplicates, on the right there might not be duplicates. It really depends on the query, and there you have to be careful to bridge these two words. That's the problem of SQL having these this back semantics or multi-set semantics, however you want to call it, whether the pure relational algebra has set semantics without duplicates. To fix that, actually some systems, or most of the systems, what they actually do is they don't use a pure relational algebra, but use a multi-set relational algebra. Because at the end of the day, you want to represent what SQL expresses. And there's some optimizations that depend on whether they're duplicates or not, and so forth. So
we are modifying our projection to also represent now duplicates.
No, you're not. You don't have operators that operate on relations in the sense of sets, but you have operators that operate on multi-sets. The input is a multi-set and the output is a multi-set. Yeah, then you're much closer to SQL. Yeah, to be fully correct, you have to do something like that. But for the sake of this lecture, I'm simplifying that a little bit and ignore that for the moment. But you're right, in order to be correct, you would have to make that distinction. Okay, so as I said, views should be handled in that step. And what you could also do, and what many optimizers do, is they replace partial expressions with pre-calculated ones. Yeah, whenever there's a computation similar to what your programming language compiler would do, if there's a plus 2 times b or something like that, it tries to simplify these expressions. So if there's constants being multiplied, you can already replace it by the result of that multiplication, stuff like that. In databases, in particular, cached or pre-materialized results can be used. So if there was a query before that did very similar or something that overlaps in the result, maybe you can reuse those results. Maybe you don't have to, for instance, here in this example, assume someone before had also a query on exactly these relations with the exact same predicate. Maybe you can reuse that result that was processed before. Yeah? There are situations where you can leverage that. But that's a longer story and leads to an entire array of interesting techniques that are handled in the core lecture. So here we keep things simple. Important for the following discussion is, I think I had a similar slide before when talking about relational algebra, and I told you, relational algebra can be read in 2 different ways. Either in a declarative way, I see an expression, relational algebra expression, and that describes what I want to have. Or I can read it in a more procedural way, saying, okay, that's kind of a function stack, a function call stack, and it's really that order that has to be applied and then the order is fixed, and it must be exactly that order. And previously, we focused a bit more on the declarative aspect of relational algebra. Now we look at the more procedural interpretation of that. So when I write down a relational algebra expression, I'm really saying, no, it has to be this order. If something is a parameter to something, to another function, to another relational operator, I first execute what's contained in the parameter and then the outside stuff. So it's really from in to out, like any function call stack. That's how we will be treating those expressions. Yeah, and another thing we looked at is this logical versus physical operators. So if you look at the Greek symbols in relational algebra, if you look at the join symbol, if you look at the sigma for selection, for filtering, that describes again what is going to be returned, but not how it's going to be calculated. Which algorithm is used to implement a specific algorithm, that's a different dimension. So when you recall, and I copied that from that notebook relational algebra back then, we always had expressions like that. So when we wanted to filter something, here we want to filter all movies on the year attribute, so returning all movies that are strictly greater, strictly younger than the year 2000, appeared after 2000. Yeah, in terms of a logical operation, that's a selection, that's filtering data. But you can't implement something that's purely logical. You have to make a decision eventually which algorithm to use. And therefore, in the notebook already you saw there was this underscore and then a different name. And that's actually denoting which algorithm is used to implement that logical operation. So in other words, we have this logical operation, the selection, and we have a physical realization of that operation, which is denoted after the underscore. And this distinction is called logical versus physical operators. Again, logical is these weird symbols, bow tie, set semantics, sigma, stuff like that. That's purely logical, not saying how something is computed. But now we need to add a bit more to that, and that is for each logical operation, we have different physical algorithms. So nested loop, for instance, nested loops or cross product is a valid algorithm to compute the result of a join. To join two relations, you can build the cross product and then pick all the tuples from the result that qualify under the join predicate. That's fine. Super inefficient, but fair. It works. The other is to use some sort of index or data structures and many other algorithms we talk about in the core lecture. And the same holds for all of these relational algebra expressions. There's always one logical operator and then a ton of physical realizations, a ton of algorithms that implement that logical operator. In other words, compute the result to what was specified or what is desired to compute with a logical operator. Yeah, that's an important distinction. So now I introduce a couple of a lot of terminology, actually, that's important for the discussion. The first is the term plan. So any valid relational algebra expression consisting of logical and or physical operators is called a plan. So in other words, it's just again, a stack or a combination of these logical and physical operators. And in contrast to what we treated in relational algebra class, here it can now be physical operators. Like in the notebook, I'm saying it's not just scan, or it's not just selection on something. I'm not just writing a sigma or something like that, and then whatever R, and then there's a join of S on join predicate, whatever R dot X equals S dot Y or something like that. Now this time I could also write this underscore-ish notation. I could say, you see that I'm plans underscore SMJ, for instance, whatever that means. Just saying this is a physical operator and this is a logical operator. And when I mean plan can be any combination of physical and logical operators, the following. Right. And an expression consisting only of logical operators is a logical plan. An expression consisting only of physical operators is called a physical plan. actually, those are 2 steps in optimization that's typical, that may be kept apart, we will see in a moment. Yeah, and once we have a plan, we have to come up with a quality of a plan. So to determine the quality of a plan, we need to develop a function that can compute or estimate that quality. In a real-life example, assume you want to go shopping. You go to a supermarket and you have 3 different options. You can go here to the supermarket on campus, you can go to the supermarket downtown, Mainzer Straße and whatnot. Maybe you can go to a supermarket in Saar Louis. There are different costs associated with all of these options. If you go to the supermarket here, maybe the walking distance is fantastic, 500 meters, but maybe the price tag of the stuff is a bit high. Not sure. Yeah. If you go downtown, it's relatively quick. Price is probably okay. If you go to Saar Louis, you have a long travel distance to Saar Louis. I don't know about the prices. So basically, you try to come up with the costs associated with these 3 plans. So you have 3 plans to go shopping, and you will be adding up, okay, it takes so much time, and my shopping cart will take that much money. And basically, you try to combine that in a number, and that number is called the cost or the quality of a plan. What is the quality of the plan? Or here, for the shopping example, you want to have a combination of the lowest traveling time plus the lowest price for your shopping cart, something like that. Yeah? Already 2 measures being combined. And that's the different ways to associate quality to a plan we will see in a moment, but that's an important aspect. In the following, what we basically do is we will create many different plans, many different options what we could do, but only go for one of those. Yeah, like with shopping, you don't go shopping to 2 of the supermarkets or all of them typically, unless you don't find a specific product, maybe that's a different story. Yeah, we want to make plans, many plans, associate costs to those plans, or determine the quality of a plan, and then go for a specific plan. And getting back to computer science, this means quality may be many different things. It could be the lowest runtime overall, or on a sensor device, it could be low power consumption. It could be that little data is loaded from the network and stuff like that. Yeah. So before we go there, some more terminology, and that is the term selectivity. So what is selectivity? For a unary operator, having one input relation and one output relation, its selectivity is the ratio of the size of its output relation R prime to its input relation R. Something like that. So in other words, if you recall this notation, that's the cardinality, meaning the number of tuples in a relation. So if you, so what we're doing here is we compute the number of relations in the input, and we have the number of relations in the output. Well, that can only be smaller, obviously, because this filter operation cannot add stuff, it can only remove stuff. So if you don't filter out anything, so if you don't remove stuff from R, every R prime has the same size as R, so this is equal 1. But typically you remove stuff, R prime is a subset of R, and then you have fewer elements here. So this is the number from 0 to 1, basically. That's the range that's being returned by this function. And that expresses, for a given filter condition, there's a size of the result set. Yeah, and then there's weird terminology coming up. Yeah, I'm just the messenger, don't blame me for that. But that's how it's defined in literature. So one is high selectivity and the other is low selectivity. High selectivity means many tuples are filtered out. In other words, many tuples are removed. Yeah, only very few tuples survive. So this fraction here is actually low. We're saying it's high selectivity. Weird, isn't it? Yeah, it's highly selective. Yeah? Think about it. Oh yeah, it's maybe an application process. It's highly selective. They're only inviting like 3 out of 1,000 people. It's super highly selective, competitive. Yeah? That's the idea of the term. Yeah? So you have a very small number here in this example. Let's assume you have here a filter predicate P that only keeps 1,000 tuples from the 1 million. So you have like 0.1% of the input data is passed on to the next operator. In contrast, low selectivity is the opposite. Few tuples are filtered out. In other words, there are many tuples make it through the filter. So here, 1 out of 2 tuples is returned, 500,000 tuples in the result, versus 1 million in the input. So that means you have a 50% reduction in size. That's important. You just have to learn it by heart. That's the terminology. Highly selective, always meaning only few tuples survive. Low selective, meaning many tuples survive the operation. Yeah, and then once you have that, then you can start thinking about, okay, which selection to execute first. If you, again, the same example here, the question is, in which order do you apply those selection operators if you don't combine them through a conjunct in the first place? But these situations arise. So you could first say, okay, again, we read it in that order, which means we first select with a Q predicate and then with a P predicate. Here it's the other way around. Here we say we first select with a P predicate and then with a Q predicate. Yeah? So the order now really matters. And then you can start making back of the envelope calculations. So in this world, you first look at all of the 1 million input tuples to remove only half of them and output 500,000 tuples. Then the next selection operator will use as its input those 500,000 tuples to remove many more tuples to bring it down to fewer tuples. How many is not specified here. So you see we have we only know here how P reducers are and Q reducers are, but we don't know their relationship. The relationship may be anything statistically. That's not specified here. So but if you think about that, okay, so basically there are kind of 1 million operations here. In the first step, in the first step, 1 million operations plus 500,000 operations, so it's 1,500,000 tuples are inspected. And that could be a quality measure for performance to say, okay, what is the effort being done in doing this kind of filter operation? If you do it the other way around, the first filter, P, filters the tuples down to 1,000 tuples, and then the second filter only has to look at those 1,000 tuples. So in terms of effort, that looks much better. Yeah? So it's 1,001,000 tuples are inspected, and that could be an interesting performance quality measure. Again, the result of both must be the same by definition, but you see the numbers, the tuples inspected by the two different orders make a difference. And that may be substantial in a real system, and therefore it really makes sense to reason about that. So that brings us to the term cost model. So what we call a cost model, sometimes it's also called a cost function, is a function that estimates the execution costs for a given plan using a suitable model. For any plan P, we define a function for this that maps the plan to some number. It can be float, can be integer, whatever unit. Important, it doesn't have to be runtime in seconds or something like that. It doesn't have to be a joule or something like that. It doesn't have to have a unit. Typically, it doesn't have a unit. The only purpose of these functions is that they maintain the size relationships. So if one plan is slower than the other, I assume that the slower plan has a higher number in terms of its runtime than the faster plan. But the absolute numbers really I'm not interested in. It's just the relationship of the different cost estimates that have to be maintained by those functions. So in the example above, we argued that the evaluation order is better because fewer tuples needed to be inspected. So the cost model that I was using implicitly there was something like that. I was looking at the number of intermediate results. So if I define my cost function like that, I take the sum over the cardinalities of the output relations of all operators in P. That would be a valid cost model. If you go back to the example, that's what I did here with this number. Yeah, so I looked at the output from this operation. How costly is that? 1 million tuples inspected. Let's remove some of these again. Yeah, so this is the result of the cost function, and that is basically the result of the costs of that operation. 1 million plus the result of that operation is 500,000, so that is the sum. And here, down there, it was the other way around. So that was my simple cost function. Yeah, and important is the note I wrote down here. So I'm using a model, and computer science is full of building models about reality and leaving away some of the information. So I'm really leaving away a lot of information. For instance, I'm completely ignoring the costs for accessing the data. Assume the data I'm filtering on sits on a hard disk, on an SSD, on a network or something like that. I completely ignored those costs. I completely abstracted over that cost. I just counted each tuple as one, no matter where the tuple comes from, on which storage device. Nevertheless, you will see that these kind of simple models often work surprisingly well. But there are also typically many assumptions being built into those models. So here's an example of other cost models that are very popular. So one is to look at the I/O costs. I/O meaning, okay, how many operations do I have to do on my storage device? Like, how often do I have to query have to ask my SSD or my network to give me some data? That's typically a very costly process to fetch data from an SSD rather than from main memory. So that's a valid cost model. Total runtime is very popular, of course, because often that's what you want to optimize for. You want to have a query plan that, yeah, it's the fastest possible query plan. Again, energy consumption could be something like that. Or in certain constrained situations, it's maybe main memory. Yeah, if you're scarce with main memory, maybe you better want to have a plan that's not as fast but doesn't consume so much memory, because maybe on that machine other things are going on and you simply cannot allocate so much memory. Okay, so but back to heuristic optimization. So now, as we have cost models defined, or the costs of a plan that give us at least a basic feeling for what a good plan and a bad plan is, because we somehow, in the back of our heads, we have this cost function, no matter how that is defined. Now we want to get from this annotated relational algebra or logical plan to a transformed logical plan. So again, what we have here is a canonical translation we had initially with all the cross products and the selections on top. And now the basic idea is that we iteratively transform that plan. Yeah, so we take the stupid canonical translation and try to transform it to a different relational algebra expression / a different plan that computes the same result, but hopefully more efficiently. Yeah, we rewrite that plan. And that's called rule-based transformation. So that's what I just said. Rule-based transformation may never change the outcome of a plan, the result of a plan, but we attempt to transform the plan until none of the heuristic rules are applicable, and we only use rules that always reduce or believe that we believe to reduce the costs under a given cost model. So we always have rule-based. You will see in a moment, it's kind of weird that the cost models are not used explicitly, just implicitly here, and the rules are basically implicitly using the cost models. Later on, we will look at cost-based optimization that use the cost models explicitly. Yeah? But the cost models here are important just for you to understand that quality of a plan may be many different things, depend on how you define it. Yeah? So for the moment, let's stick to the idea that we want to lower the execution time of such a plan, and that's what all of this is about. And here's a super fancy, crazily complex algorithm, 2 lines. So what does it do? This is rule-based optimization, and it takes as an input initially the canonical plan and a set of rules to apply to such plan, and then it iterates over that like crazy and modifies that plan. Yeah, so you see it here. So the input plan is modified using so-called rules. Yeah? And it's rewritten and transformed until this condition strikes. Yeah? So as long as any rule in that rule set matches, you transform, but eventually you reach a point where you can't transform the plan anymore. Yeah, you tried all your best, but now you have a plan, you can't change it anymore, then this algorithm stops. And before we look at the extensions, let's look at a simple idea of such a rule. So this is always a match and a modify part. So the match part is basically a pattern matching on the input plan. I'm calling it an operator tree here because basically that's what it is, but I mean the same thing as the plan. So you try to see whether the input plan matches a certain pattern you can do something about. Is there a certain pattern? Is there, maybe if you're specialized on a selection, to rewrite the selection to anything, you're looking for selection. If you're specialized on cross products, you're looking for cross products. So you're searching for that specific pattern and whether you find a match on that input tree. So it's basically a predicate telling you, yeah, I have a match on that tree or I don't have a match. And only if this matches, if this predicate returns true, you actually modify the input tree. That's the actual transformation that changes the input tree and returns the modified input tree of primacy output. Example, so a match could be something like, is there a selection with a conjunction in the predicate? We see that sigma operator A and B, and you can break that up into two selections. Doesn't hurt, doesn't make a difference. So you could break it up into two operators, into two selection predicates with two separate selections. Maybe that gives you some optimization options later on. Or another example, is there a selection with a joint predicate directly above a cross product? We will look at that in a moment again. But this is a rule allowing you to combine selections and cross products into a join. So this is basically inverting this alias we defined for joins. I said, when we defined the join operator, I said, yeah, a join is just basically syntactic sugar for, you could express it as cross product followed by selection on the join predicate. This is kind of reverting that. It's basically rewriting it to a real join operator. So let's look at that one by one. And let's do that also simultaneously in the notebook. A really nice notebook on that, where you see that in action. So we use the relational algebra library as in previous lectures. So again, the IMDb snapshot with some sample data. I don't have to show that again. So we have our relations. Indexes we don't need here. And then we have our unoptimized plan. This is the canonical translation of some SQL expression. SQL expression with two tables in the from field, a couple of where conditions, and then this, what we see on top here is basically in the SQL statement, what's after the select. So basically these two attributes, last name and prop, is in the select. So that is how we start. And now we will iteratively rewrite that plan to something that we believe is more efficient. And that happens here. So the first is we break up the end, the conjuncts. Where do we have it? We have one here. This is a conjunct. Oops, I can't mark that somehow. So here's our end. Right? See that? So that's the conjunct. We couldn't break that. We could break that up. And that's what we do here. So again, this is what we see before applying the optimization. And that is, in the notebook you see we have this break up selection rule. And then we can, so where's the projection? So the entire plan is called PROJ for projection. Then you feed that into this selection rule, you call optimize, and then you display the graph, and then you see something like that. And then you see, okay, now we have these two split into two different operators. Does anyone see a reason why I even want to do something like that? Yeah?
I rather wanted to ask, why would you ever want to split an AND? Because the AND kind of makes it finer. So I guess we are filtering out more
Yeah, but there's a specific reason why that may apply. Maybe it's unclear from what you know so far, but you will see in a moment why that makes a different sense, why it makes sense. A simple scenario is that one part of the selection is on one relation and the other part of the selection is on another relation. And we will soon start pushing these these filter conditions down the tree. Yeah? So basically, bottom line, I do that as a facilitator for rules that are coming up, rules you don't know about. So you can't meaningfully answer my question actually at this point. It's a preparation step for other optimizations I will now do in the following. Yeah? So I split this up. Because now comes the mother of all rules, and that's called predicate pushdown. Yeah, so again, here's our start situation. Yeah, we split it up. We have a couple of selections that are all sitting on top of this cross product. And now when I apply push down selection, I end up with a situation like this. Yeah, so see, okay, you have now the selection is not on top of the cross product anymore. This is not there anymore. This is here, this is there. Yeah? And if you go back, we had Tarantino and probability smaller 0.7 in this same conjunct. Yeah? Now, as I split it up, I could push the one to the left and push the other to the right. Wouldn't have been possible if I hadn't done that. Yeah? But basically answered that question. Yeah? Sometimes you split it up and it doesn't make any sense because it goes down to the same anyway. Yeah? So if you think about that, what you could do now, of course, is you could recombine those into one expression, for instance, probably more efficient. Yeah. Okay, but why is it a good idea to do something like that? Why is it a good idea to push down these selection operations towards the data sources? Yeah?
I believe because the cross product is very expensive to compute.
Yes, cross product has square complexity. We will get rid of that in a moment. But no matter what happens on top, my goal here is to reduce the amount of data that's flowing from bottom to top. Because it's for sure that the more data that flows up, the higher the costs for whatever I'm going to do. So I try to get rid of data as early as possible, not only after the cross product, but before. Yeah? So it's filtered out already close to the data sources and not only on top of it. Yeah? So I try to really remove stuff early. And this is a more formal description here on the slides. It's really the most important rule because it's being reinvented, I guess, every year or so in some place of computer science. So let R1 and R2 be relations, P is a predicate, and this function returns the attributes on which P imposes conditions. Then we can formulate the following optimization rule. And this is again read as, I'm not sure whether I used it in this lecture, I don't think so. These are the conditions that must hold, and if those conditions are held, you can do this stuff. So basically again, on top you have this match part. If you go back to these definitions, match and modify, this is a different way of writing that. This is match. If all of that matches, we can modify it like that. In other words, we have a selection operation on a predicate, and here we have a join or cross product. That's what this is trying to express. So I'm trying to define it for join, for a binary operation, in particular a join or cross product for both of these situations it holds. So we have this situation that, let's assume for the moment this is a cross product. You have a cross product on two relations and filter followed by a selection. And if the condition holds that this operation is either a join or a cross product, and this the attributes that P uses, the predicate, this is written like A equals 2 and B equals C or something like that. Here, this condition says all of these attributes are only with respect to R2. Could also be R1, that's the same story, but here it's only with respect to R2. So I'm not in a situation where one of the attributes is from R1 and the other is from R2. They're both with respect to R2, or all of them, no matter how many they are. So if all of these conditions hold, I can rewrite that tree, I can rewrite this one to something like that, saying, okay, I first apply the selection on R2, and then comes the spiny operation, cross product or join with R1. Yeah, that's basically what this rule is saying. So I'm pushing down the selection operation. I'm pushing it through the cross product or through the join operation. So here's a more colloquial way of saying it. Selections should be pushed down as close as possible to the data sources, so down the plan. Yeah, and this is being reinvented all over the time. I mean, I heard about a startup, I think it was in Hamburg, that basically the major business idea of them was, oh, we have all these satellites, and the satellites do all these images and send the images down to the ground station, and that's a lot of network traffic. What if we filtered out those images directly on the satellite? Yeah, so rather than sending all the images down to Earth, and then running operations on the images, you could ship the operation up to the satellite, filter it on the satellite, and just send down the filtered data. This is also an example of predicate pushdown, just geographically. It's the other way around because the satellite is up, sending the data down. Yeah? So it's actually kind of misleading here. But it's the same idea. You filter the data close to the data source, or here close to the collecting device, the camera in the satellite, and filter it there already, and then you save so much bandwidth and computational power on the ground station. For sensor data, it's a similar thing. Yeah? So assume you have a temperature sensor in the room, and every minute it measures the temperature. So why do you send it every minute? You could send it when it changes. Maybe it's an easier idea. Yeah? Just change if there's any, send it if there's a difference. Mail protocols like IMAP, you have the option to filter on the server versus filter mails on the client. Yeah, for a large folder hierarchy of mails, maybe it's so much easier to filter it on the server and just send down the qualifying mails down to the client. And that's the general pattern in distributed systems. Yeah? So in the distributed systems, they're often limited by network traffic, sending something over the wire. And that's a very good strategy to filter stuff on the remote system and just send over the results. That's another example of a predicate pushdown. And yeah, very interesting example is also what's called smart disks. There are many names for that. A more recent name is PIM, or processing in memory. The idea here is, I mean, if you think about the von Neumann architecture, we have all these memory, types of memory, this memory hierarchy, and then we have the CPU sitting in the middle. That's super simplified. It's more something for the core lecture, but just to so whatever, you have an L1 and you have L2 caches. Eventually you have whatever, DRAM. And to do anything in such an architecture, you first have to transport data from DRAM or further down SSDs or stuff like that up to the CPU. And then once the data sits in the registers, you can do something. You can filter data, which means if you want to filter a terabyte of data, you first have to transport it over the bus system of the architecture to the CPU, filter it out, and then send the results somewhere. And here it's the same idea. You could push it down in hardware. So there are approaches that allow you, and that's called processing in memory, that allow you to filter out stuff in the hardware memory already. And if you do that, you don't have to ship all of the data to the CPU, but maybe get rid of maybe already a huge chunk of the data and save bandwidth in this space. That's called processing in memory. It exists in many, many devices. You have it for spinning disks, you have it for SSDs that can do pre-filtering, pre-aggregation, stuff like that, and also for DRAM these days and other devices. It's the same idea, it's a predicate pushdown. So I continue with slide 24 at this point. So this is the rule we already learned about, that we can break up a conjunct into two different selection predicates. So I showed that already in the notebook. But here, this is very important, also maybe the second most important rule other than predicates, and that's basically saying Well, if you're in a situation like this, where there's a cross product, and yeah, please, let's get rid of the cross product because it has a square complexity. We not want to run this as a cross product. It would be insane in most situations. Then we look at situations where we can express that as a join operator in relational algebra. And that is a situation where this predicate is a very special predicate, a joint predicate. And the joint predicate has this property that one predicate in that predicate refers to one of the inputs, R1, and the other, and some other part of the predicate refers to the other inputs. So it's a phrasing condition on both of the inputs. And if we detect such a situation, we will write it to such a join symbol. Yeah? So we really get rid of this cross product. And if you look at that in our notebook, you can see it in action. So that is, again, the initial situation. And now I use this rule. So again, here, cross product. And here is a joint predicate directly on top of the cross product. And now I'm fusing these two operators into a single join operator. You see it here. Now we have the bow tie symbol here, and the joint predicate is a parameter to this join operator. And why would that make any sense? I mean, I told you this join operator is just syntactic sugar for a cross product anyway. So if you read the relational algebra slide carefully, you would say, yeah, okay, man, the join, that's cross product followed by the selection on the joint predicate. So what's the point in using the extra symbol in such a plan? What's an idea? Yeah? Yeah, I can filter out while doing the cross product. That the argument is right. Well, let's say it's not wrong. That's okay. You can directly, while building the cross product, you can make a decision whether you produce a result to the cross product, so to say. That is more efficient than building first the cross product and then filtering out. However, in terms of complexity, if that is your measure, it's still the same square complexity, because you're combining each tuple from R1 with each tuple from R2. So on the complexity side, you don't win, just the constant side. Yeah?
I mean, didn't we say that when we're doing the join, or when saying to do the join, we don't actually do the cross product, but we do something different that then it's the same?
Yeah, that's the interesting question. Yeah, I do something where I believe, I mean, I'm doing the rewrite here to this join symbol, but if I now use that to again replace it with a cross product thing, I wouldn't gain anything. So the hidden assumption is that maybe there's something smarter you can do to compute the result to a join rather than doing the cross product and then filtering out. Yeah, that it goes a little bit in that direction. And the answer to that is yes. Yeah, so you can do joins in linear, n log n, time, depending on the situation. But typically you have something that's close to linear runtime rather than square. Yeah? For hash joins, you can do that, for instance. But that's a different story. So, so that's one thing of the answer. And the other is what I presented to you at the beginning of today's lecture. If I go back to the slide, where was it? Here we go. Logical versus physical operators. So yes, I'm currently showing just this bow tie symbol, but planning here is not only about relational algebra. In planning, I can also make the decision to say, okay, now I really want to use a specific algorithm. Yeah, I want to make the choice for a specific algorithm that's more efficient than the standard cross product. So planning will factor these things in. It will try to pick algorithms that are more efficient than blindly doing a cross product. Yeah? And that's a big part of the story here. Okay, where was I? 24? No, I wasn't there. 27? No. Somewhere it's genau. Yeah, so this is an important rule, trying to get rid of these cross products. And there are variations of that rule, but you can read that back home. Yeah, so that's basically you could say that's kind of the end result of such a plan, but there's another optimization that's sometimes done, and that is to create additional projections in such a plan. In our slide set, this is on slide 21, and that's called a projection pushdown. And that is a situation where you either push down a selection or you add additional selections. Without going into the formal definitions here, let's jump directly into an example. Assume you have these two relations, R and S, defined with those schemas here. And the original expression is something like this. So it's a join, foreign key join on R and S, and then there's a projection. And now we rewrite that to the following. We say, aha, before doing the join, we first do the projection here, and then we do the projection there, and the result goes into the join. So we add additional projections. I'm not touching the final projection here of this plan. I'm just saying, aha, what I'm doing here is I add another projection here and then add another projection there. So additional projections are introduced that project attributes away as early as possible. Why would that make any sense? Yeah, making the plan more complicated, so to say. I'm adding more operations rather than simplifying. I go in a different direction. Yeah.
We are avoiding the costs of the join, which are much more than projections.
We are not avoiding the costs of the join. The join is still there, right? It's the same join predicate as before.
We have a lot less. We expect a lot less tuples in this situation than in the previous one.
No. No, we project on the ID on R, so we cannot reduce the number of tuples on the left. Yeah. On the right, we project on R ID, C, which could reduce because R underscore ID, C is not unique necessarily in C. That could happen. Yeah.
We have as many tuples, but we have less columns or less.
Exactly, that's the right answer. So I'm narrowing down the data. It's less wide than before. I'm removing columns. I'm removing the attributes that don't play a role in query processing anyway. I'm not interested in those attributes. Yeah? So the query is saying on the top level, okay, I'm interested in attributes A and C, and whatever attributes exist in those relations R and S, I don't care. So it's kind of a variant of projection of selection pushdown, just rotated by 90 degrees. If you want to look at that like that. Yes, some of the attributes, all the fluff that comes with those tuples is removed. Yeah, so I'm removing all the attributes that don't play a role in my computation. So if for instance, R has the attribute B. Yeah, we see it here, this attribute B. Who cares? No one cares about that, so I'm just returning ID, A. And similarly for S, I'm just returning RID and C, but not D. D is removed. And like that, it has the same or similar effect as selection pushdown, in that less data gets processed and gets hangs around in memory and in the processing pipeline. No? So that's something that you could also do. And if you do it here in our example, in our notebook, so again, this is a start situation. We always repeat the start situation, and then the second step is adding those projections. Well, yeah, so now we have them in blue. We add those projections here all over the place. And you see already why typically this is not done, because it blows up the size of the plan dramatically. It gets pretty much unreadable. Huh? So in principle, you should do that. You should insert those projections. For practical reasons, the assumption is often that you do it anyway, but you don't denote it in the plan explicitly. Yeah? So you will do that. You will remove away attributes whenever possible, but often you see plans where we don't annotate that explicitly. Okay. Yeah. There are a couple of other rules we wrote down. Yeah, maybe this one. So join, union, intersection, and cross product are commutative and associative. Yeah, that's an important rule that may be useful. We will look at that next week actually. It's kind of unfortunate that this rule exists. It's very unfortunate, and this as well, because it allows you to play with the order in which you execute the joins. We will look at that next time. Selections are changeable. That's what we learned already. Right. Yeah, so much about this rule-based optimization. Take a look at the notebook, play with that. You can also create your own plans. It's a very powerful technique. It leads you very far. Initially in the history of databases, products actually only did this simple, what we now call in 2025 a very simple way of optimizing, but it gets you very far. You can do many things with that. You can dramatically speed up query processing in many situations. Some others you will miss, but that's what we learn about next week. Okay, but there's another important optimization that an optimizer must do. And with that, we briefly have to remember what we learned in slide set 2, slides 33 and 35 to 35, and that was about this horizontal partitioning. I explained it along the lines when talking about grouping. You group an input relation into sets, into subsets, and they are called horizontal partitions. And that is the definition we use. This is the definition I used for that. So you have an input relation, and then any assignment of tuples from R to relations R1 to Rk is called a horizontal partitioning of R, or for short HPT. If for all tuples in R there exists a partition where that tuple resides. So you're not going to throw away tuple, you make sure that the tuple ends up in one of the partitions at least. So we had it here. In those examples, all of the 4 tuples end up in one of the partitions here and there, but not there, because as here we're losing the red tuple 7.b. Yeah, and with that you can define a disjoint horizontal partitioning, which means that pairwise all partitions are disjoint. Then we treated the partitioning function in that slide set, and okay, you can define a function allowing you to determine what is a partition. So we had this modulo function as an example. So if all of your inputs go through modulo function, you end up with 2 partitions, one where this returns 0 and one where this returns, 1. Yeah, you see it here in the index. You see it here. Yeah, that's basically the different return values. Or you can define a partitioning function on whatever, an attribute value. You see it here. And with that, you end up with certain partitions. And that's then called induced horizontal partitioning. Yeah? Basically, given an input relation and given a partitioning function, you induce a certain partitioning of the data. You induce 2 partitions here, one where modulo returns 0 and the other where modulo returns 1. Here on the right side, you reduce partitions that are defined by this value of the B attribute. Yeah? If the B attribute is A, you end up in this partition. If it's capital B, it's here, capital C, it's there, and so forth and so forth. Yeah? We have that in slide set 2 when talking about partitioning. And based on that, we now define an induced recursive horizontal partitioning. So we apply these partitionings recursively, which means we don't have a single partitioning function P0. P0. Come on, you always switch this pen off. P0, but a sequence of partitioning functions. And I would prefer to explain that by an example again. It's the same example as from slide set 2. We only have these 4 tuples as an input. We have the same 2 partitioning functions here. So P0 is the model operation and P1 is returning the value of B. And now the partition labels define the return values of these 2 partitioning functions. So 0 means, P0 returns 0. And the second A means, P1 returned this capital A. So all of the elements in this partition, all tuples in this partition R0, A, have that property that when you apply those partitioning functions, the return value of P0 is 0 and the return value of P1 is this capital A. Yeah, I'm just applying the partitioning recursively here. And that yields a super important concept, and that's called an index. Any set of recursive or non-recursive horizontal partitioning functions that can be used by a query to reduce a query search space is called an index or index structure. Yeah, index is just a database researcher's name for data structure. Yeah, if you learned about binary search trees, hash tables, red-black trees, and what exists, zillions of data structures out there, I will be calling those data structures indexes. And the major property of all of these data structures / index structures is they define recursive horizontal partitionings induced by partitioning functions. And why is that interesting? Because for query processing, well, we can exploit it like crazy. So if you have a schema like this, with 2 attributes only, and you already partitioned this data using these 2 partition functions again, yeah, maybe you build those 1, 2, 3 partitions, then you can start rewriting your queries. If you have a query like, okay, I want to have all the data where the B attribute is equal to capital C, well, that is equivalent to not using the entire relation as the input, but just the partition where the output of that second, so of this P1 partitioning function is capital C. Because now that's an invariant. Yeah, I'm writing down an invariant with these partitioning functions saying, okay, the invariant, and that's another way of reading that. Yeah, this is an invariant saying for all tuples in this set, the modulo partitioning function returns 1, so all of these numbers are odd, 7 and 1 are odd, yeah. And the second attribute is a capital B. So that's an invariant I'm writing down here. And that's what I'm exploiting here. I'm saying, okay, if I know about these invariants, I don't have to process all of the tuples from R. I only have to inspect the tuples in R0, C, and I get the same result. By definition, it must return the same result. Here's another example. Assume you have A equals 7 as a condition. Well, cool. Yeah, I only have one. Maybe let's remove some of these. So only one of my partitions has an 1. Here, there's a 1. This is a 0. So by definition, that cannot be part of the result. That cannot be part of the result because the number is even. As I'm interested in A equals 7, which is odd, I can directly replace this R by R1, B. Yeah, and that is a much smaller input result. So here I'm only filtering on 2 tuples rather than 4. Yeah, here it was 1 tuple rather than 4. Other example is A equals 8. Well, yeah, that's an even number. I have 2 of those partitions which contain even numbers, that and that. So I could also process on the union of those 2 partitions. Still, I'm only filtering on 2 tuples rather than on 4. Yeah, so I'm rewriting against a smaller set of horizontal partitions. And that is at the core what every data structure does. No difference whatsoever. And the art is to, in the query optimizer, to detect these partitions and do something with that. So in this lecture, we look at 2 types of queries only. So one is a point query and the other is called a range query. Point query means you have a predicate like this. There's an attribute A equals a constant. So A, capital A, is some attribute from the underlying relation, and C is a constant. Yeah, for instance, foo equals 42 or something like that. Yeah, foo equals 42 could be the condition. That's called a point query. I'm interested in a specific point in my data. In contrast, a range query specifies an interval. Yeah, so you say something like that. So the value I'm interested in should be in the range from low to high. Yeah, or you could also write it like this. It looks more like as you would write it in SQL. Low, smaller equals C, smaller equal high. Or you can also make it open or half open and write smaller, strictly smaller, stuff like that. Yeah. And this is called a range query. And a database system now has certain indexes built in to facilitate answering these kind of, or computing results to these queries. One is hash tables. You should have bumped into in the data structures class. That's very suitable for point queries, though it can be extended to range queries as well. Then the second most important structure is B-trees. That's suitable for both point and range queries. And another is bitmaps. So bitmaps, oh, it's not writing anymore. Oh, iPad kaput. So bitmaps, we're not going to look into it. B-trees, we'll look into it in a moment. Hash tables, you should have learned about in the data structures class. But where's binary search trees? You learned about binary search trees, right? Why isn't it here?
I learned about it, but I don't remember anymore.
Okay. Actually, it's a very, I mean, there's so many binary search trees and rotations and red, black. I think it's a very good algorithmic exercise to get going. How do algorithms work? How do you prove stuff and the complexity stuff? And so I think it's a good exercise. But now I'm telling you, hey, there are three important index structures, and actually the third is kind of optional already. The first and the two that really are important. So database systems don't care about binary search trees. How could that be? So there's an idea. Yeah?
Maybe because you don't search for a single entry, but like multiple ones. And maybe like binary is too weak, maybe you need like ternary or so.
Yeah, the last sentence points in the right direction, but the first sentence, so binary search trees also complexity-wise are perfect. Yeah, you can build these optimal trees with log-n search capabilities and whatnot. But the main issue with binary search trees is that they don't map well to storage, to the storage system. Most storage systems have this weird property that they organize large chunks of data called pages. Pages could be whatever, 1 kilobyte, 4 kilobyte or something like that. And in comparison, a node of a binary search tree is super small. A couple of dozen bytes if it's a big one. It doesn't really map. The two worlds don't really map. And therefore, we try to use something different. And one of the most important structures in that space that works super well on storage is called a B-tree. And a B-tree is an n-ary structure, yeah? But not for the reason to be more efficient in terms of computational search, but just for the reason to make the nodes bigger, yeah? And make the nodes map to those storage pages. And we only have two types of nodes. One is called internal node, or nodes for short, and the other is called leaf node, or leaves. And B-trees are a bit weirdly defined. I mean, depending on which variant you're looking at, it's even weirder or less weirder, but more or less it boils down to the idea that these nodes and leaves are always assumed to be half full. Yeah, you try to store data in these trees that it is occupied at least by 50%. And that is why you get these weird definitions. So a B-tree is an n+1 array tree. N is greater equal 1, which means it could also be binary, partially at least. It has two types of structures, and the n is either from this interval that you define at some point. You have to define a k and a k star. That depends on the sizes you're targeting at. We'll see that in a moment. But it must be in that range. So it's not from 0 to k -1. It's from k to 2k. And the same holds here on the leaf level. It's k star to 2k star if it's a leaf. Yeah, so it's a half full property. Maybe let's look at an example again. It makes it easier to understand. So here's an example B-tree, and here I picked k to be 1 and k star to be 2, and it has 3 levels. This is a root node here, and you see these inner levels. It's always keys or pivot elements, and then there's a pointer to the left and to the right. That means if you see a key here, like here in the example, you see 2 keys, there must be 2 outgoing nodes plus 1. Always one arrow goes down, one arrow more goes down than there are keys in these inner nodes. Yeah? So we have 2 keys and we have 3 of these arrows. And that is propagated recursively here. That's another inner node. You see 2 keys and 3 arrows. Yeah? Then here we're on the leaf level. Here it's basically key value. Here you have as many values as you have keys, and each key is associated with a specific value. That's the core structure of such a tree. Right, and maybe let's talk about some of the invariants of such a tree. I think that helps understand it. So basically what a tree does is, it represents a certain key space. So those are your keys, and keys are picked from a certain domain, and the entire tree represents the entire key domain, from -infinity to +infinity, excluding. But if you recurse into that a bit, you see what such a node actually does, is it partitions the data in this example into 3 different subspaces. Yeah, the node says, okay, if it's strictly smaller than 43, all data that's strictly smaller than 43, and that is a contract this node makes, if it's strictly smaller than 43, it must be here. It must be in that part of the tree. If it's greater equal 91, it must sit in this part of the tree. If it's 43 including to 91 excluding, it's in this part of the tree. So here's again the recursive horizontal partitioning property we've seen before, just with one single recursion step. That's one recursion step I'm applying here. Not multiple ones, just one. So what you're seeing here is a root node pointing to 3 different trees, to 3 different sets. And now I can recurse into that, and I could say, okay, the blue boxes, I can partition them further through a different recursion step. And that's what I'm doing here. So I'm not touching this property, this invariant. That's untouched. Now I'm just saying inside this blue box, I'm recursing. I'm again applying a second level recursion or partitioning and say, okay, here I'm partitioning this again into 3 regions, that region, and that region. Where for all of the data, of course, this still holds. Yeah? No data must be strictly smaller 43 or greater equal 91. That's not allowed. And that explains also the boundaries here on the left and on the right. Yeah? But I'm basically just what I'm showing is simply a recursive partitioning. But what's the relationship to the induced horizontal partition, recursive horizontal partitioning I showed before? What is the relationship of this to this partitioning? Yeah, when you look at, what slide was that? Yeah, that's how we started, induced recursive horizontal partitioning. And I said, okay, we have a couple of these partitioning functions, and then we can apply that, and then we end up with these partitions somehow, yeah, yada, yada, yada. And then we talked about indexing, and now we end up with something like that. So what's the relationship of the 2 concepts? Obviously, we also have these partitioning functions. However, they are formed here. Maybe they are hard-coded somehow. These keys in the root node, 43 and 91, are picked somehow. That defines a partitioning function. Each of these nodes comes with a partitioning function. An element comes in, and you partition it to one of these 3 sets. That's fair. But what's the relationship of those slides? This slide and the other slide. Or in general, what's the relationship of partitioning versus any data structure?
Maybe that it is horizontal disjoint partitioning.
Yes, it's horizontal, recursive, horizontal, disjoint. Did we forget any adjective? I hope not. Partitioning. Yeah, that's fair. That's correct. But it's a bit more than partitioning. So what does a data structure do? What does an index do? It's not just partitioning, right? Yeah. It's ordered. That's true. The B tree, the partitions are ordered. Yeah. That's true. Yeah. Yeah, we have a reference to the partitions. That goes in the right direction. So we maintain the partitioning. We maintain the recursive partitioning. It's not just a matter of calling these recursive partition functions somehow. We have references. We have pointers to those partitions. And that makes the index efficient. Yeah, because in this example, how do you search such a structure? Well, you start with something like that. If you start with a specific key, well, it's always a matter of finding, okay, which partition do I have to look? It's like back home, you know that's in that closet, there's the stuff you're looking for, and there are 3 drawers. But the question is, which drawer do you have to open? If there's no meaningful label on those drawers, you have to open all of the drawers and search through all 3 drawers. But here the drawers, the stuff you pull out, right, whatever, has a label. So you only have to open one of those and then search through one drawer only. And inside the drawer is another drawer. Yeah? So basically, once you do a search, for instance, assume you search for 42, of course. Yeah? You know, okay, it can only be here. If there's a 42 in my data, it's on the left side. I can ignore all of this stuff. This reduces the search space already down to 1/3 on average in this example. Yeah? And then you go on like that recursively. So the main idea of a data structure or index structure is not only to have this sequence of partitioning functions, but also to maintain it, allowing you to keep a structure, a data structure, keep pointers between those partitions, allowing you to do an efficient search. Right. Yeah. So the B tree has a couple of interesting invariants. So each node implicitly creates horizontal partitioning of the data. Check, we had that. At all times, the node or leaf is at least half full. Yeah, that's a rule. The path from the root to any leaf always has the same length, so it's a perfectly balanced tree at all times. So there are maintenance algorithms that make sure that is true at all times. It's a perfectly balanced tree, similar to what you learn about in red-black trees. What is the other thing called? AVL trees, and all these balanced binary tree structures. So this is also balanced. The path from the root to any leaf always has the same length. Yeah, that's a balancing property we had. And entries inside each node and leaf are sorted to allow for binary search inside a node or leaf. Okay, interesting. What does that mean? So talking about the search operation. So you use this tree structure to run down these arrows and find the partition you're interested in. But once you hit a partition, you still haven't found the particular entry. So here inside, this is basically an array, a sorted array of data. Sorted array of data, you can do binary search, that's it. Yeah? So the outside structure is used to identify the suitable partition here, and inside the partition, you're doing binary search to speed up search. That's how this is used. And that's why you keep the data ordered inside such a leaf node, keep the data ordered by its key. Yeah, and then there's this other rule we didn't talk about yet. Each leaf has pointers to its left and its right sibling or subtree. We saw it here already. So it's not, strictly speaking, it's not a tree. It's a graph structure. So the tree doesn't really work here because you have these extra pointers here. So from here you can jump directly here, or from whatever here you can jump here and here and here. Why would that make sense, or why would that be suitable? To have these extra arrows. Only on the leaf level, you have this You have all leaves, that's another way of phrasing it, all leaves are in a linked list. You have a linked list of the leaf nodes. So it's basically two data structures superimposed. Yeah, you have this n-ary tree built on the leaf nodes, yeah, which leads to extra internal or inner nodes. In addition to that, all leaves sit in a doubly linked list. Yeah, the elements of that doubly linked list are the leaf nodes. Why would that make any sense? Yeah?
You, for example, go to
A bit louder, please.
if you want to search all elements in the blue partition, then you can just jump from one of 3 leaves to the other.
Yeah, if you search all elements in the blue partition, you can jump from one leaf to another. Can you come up with a situation where that might make any sense? This is dangerous. It's loudspeaker there. Yeah?
Maybe I just want something like filter out people that are born after some dates, and
Yeah?
maybe I want like basically a start point that I search, and then after that I just return the whole linked list that's on the right side of it.
Exactly. Very good. That's a use case, and we had a name for that. That's called the range query. Yeah, if you search for a specific value like 42, it's called a point query. But what you were just saying is maybe everything greater C, or maybe whatever. If you look for whatever certain birth year, then you're interested in whatever. Something like that, yes. So this is not a point query, that's a range query. Everything strictly, it's smaller, y is on the wrong side, of course. Yeah. So y greater 984, something like that. That's called a range query. And how do you execute a range query? That is easy. Where's my example? Here. Yeah, for instance, we look for range everything in a range, let's say 62 to whatever, 98. Yeah, here's my range query. How do you do it? You translate that into a point query on 62. That's the first thing you do. You run down the tree. Okay, you start here. 62, okay, it must be in this partition, in the blue partition, obviously. Then in the blue partition, you find out, oh, it must be in this partition, obviously. In this leaf node, you do binary search, you find out, it's this entry, right? This is the first entry. And then you keep on scanning or iterating over the leaf level, jumping from one leaf to another until this condition on 98 fails. Here it failed, so this is not going to be returned anymore, but everything till then, till that point is returned. Yeah, and that's how you could translate a range query relatively easily, and that is the reason why you keep this linked list on the leaf level in such a B tree. That's also the reason why in literature these trees are sometimes called a B plus tree. B plus tree. In databases, you only say B tree, but we mean B plus tree. When I say B tree, I always mean B plus tree because it's clear a pure B tree as of literature wouldn't make sense. A pure B tree doesn't have these links here. Okay. Here's another notebook that plays with the idea, if you're interested, play with that, basically using your file system to create a B tree style index. Yeah, to wrap up, so we talked about different types of models today, and I just want to show this slide because I'm seeing very often that this goes wrong in many discussions. So in computer science, we tend to build models. Yeah, a model of reality. We abstract over something, like in the cost models, if you think about that, what we did today, we counted the number of tuples that go into an operator, completely ignoring the true computational costs for filtering a tuple or fetching it from storage or something like that. Modeling is one of the most important techniques in computer science. But there's this famous saying, all models are wrong, but some are useful. And that means all these models simplify. So all models are wrong when it comes to aspects they're simply not modeling. They removed from the model. But the problem that I'm often seeing is that people confuse the model with reality. Yeah? So reality is one thing, and modeling and simplifying, having a model for that is another thing. So therefore, it's super important whenever you model something to compare the model with your reality. For instance, for this lecture, we have cost models. Yeah? The cost models should reflect the costs of the plan. If those costs are meant to be the runtime, well, it would be a very good idea to once in a while actually measure the execution costs of those plans, yeah, plot them. Yeah. So if there is time, yeah, and then basically maybe you have some parameter foo here on the x-axis, and then you're running your query, and that's the runtimes you're observing. Yeah, that's the real runtime. Maybe that's the implementation, that's the experiment. But if your cost model is something like this, has a different slope, and maybe it's not even, this induces like a linear relationship. Maybe it has some flattening here, whatever. If that is your cost, if that is your model, well, then you have a problem. Yeah? So the idea of modeling is whatever you're trying to model should match the experiment or should match reality. And it's very important to do a reality check and compare the two and whenever you're modeling. Yeah, so certain things are simplified or omitted in a model in order to bring out other things. Yeah, and that leads to this very core of abstraction. What is abstraction? A thinking process of omitting details and transferring them to something more general or simple. Yeah? And of course, you always abstract with a certain purpose. Yeah? If I have a simplified model in this lecture, I have a purpose. I want to model execution time. I want to model memory. I want to model I/O costs. But I leave so many things away. Yeah, I really invite you to read a little bit about that, because it really clarifies what a model is and what it not is and what reality is, and to please not confuse the two. That's really important, not only in databases but also in other fields of computer science. Yeah, as usual, there's more material on all of that on my YouTube channel. Next week, we will continue with cost-based optimization, heavily building up upon this week's material. So make sure you understand this week's material. See you next week, Thursday. Yeah? Have a good holiday on Thursday. Thanks.